So, hello everyone again. This is lecture number 2 part 1 of alternating current. In the previous lecture we have started with the AC voltage applied to an inductor. We will start the further discussions regarding that topic only, and then we can move forward with AC voltage applied to an capacitor and so on. So, this is lecture 2 part 1 of alternating current. I am Sameer Lavankar. Let us begin our discussion. So, just a course outline for you, the things which we have completed till now. We have completed with the introduction part, in which we understood basically what is the use of AC currents or basically AC voltage or basically AC circuits. How are these different from direct current? What was the advantage of using AC voltage or AC currents with respect to DC voltage or DC source, etc. And then we move on to the second topic regarding the AC voltage applied to a resistor, in which we understood basically what happens when there is a single resistor and a single AC source or AC EMF being applied. So, we basically calculated that, let us say if the voltage is Vm sin omega t, we got that the current is also Im sin omega t, where Im is Vm by capital R. While deriving all these things, it was being assumed that there is no internal resistance being available, and the only voltage across the resistor is only due to the resistor capital R. After this, we have concluded with the new discussion that which was regarding the phasor diagrams, in which we basically understood as in how a phase angle or difference between the movement of current and voltage can be described in terms of a normal coordinate system, as in circular diagrams, which are called as your phasor diagrams. These phasor diagrams are not as that important for AC voltage applied to a resistor, but these are very important when we will understand the subsequent discussions such as inductor, capacitor, series LCR circuit, LR circuit, LC circuit and so on. So, that was necessary for this. We can even make a diagram for AC voltage applied to a resistor, but that is not so significant, that is not so important, but one should also remember that what is the basic diagram for it. So, basically let us suppose if this is your V, so then this will be I. So, this is basically a phasor diagram for an AC voltage applied to a resistor. Fine. That thing being said, now let us start again with the discussion regarding AC voltage applied to an inductor and then move on. So, AC voltage applied to an inductor. So, basically what is inductance, what is self inductance are already been explained to you in previous chapters. We will just go directly again. I will try to derive the equation I got in the last lecture again, and then we can move forward. So, basically it was till this point we already know that V minus L di by dt is 0. Now, we can write this equation as di by dt is nothing but equal to V by L, and we know what is V. V is basically the EMF being supplied, and that this EMF being supplied is nothing but Vm sin omega t. So, just writing that here. So, it is nothing but Vm by capital L sin omega t, correct. Now, we need to calculate the value of I. So, basically integrating both sides with respect to t. Or with respect to time, which is t, we get so it is integration of di by dt dt is equal to integration of Vm by capital L sin omega t dt. So, this dt get cancelled, integration of di is basically I, which is nothing but equal to Vm by omega L minus, because integration of sin is minus cos omega t, right, and then it is plus constant. Okay. So, this was the equation I already derived in the last lecture 1 part 3. Now, let us move forward, let us try to understand what is being explained here. Okay. So, first of all, if you see clearly, there are two parts being derived here. One is this part, which is basically Vm by minus Vm by omega L cos omega t, and there is the second part, that is your constant. Okay, going with the dimensionality, the dimension of this constant is basically current, correct, because if the dimensions of left side is equal to right side, that means that the constant is also having dimensions of current. What does it mean? It basically means that the integration constant has the dimension of current, and also it is time independent. Okay, so let me just write that line also, that it is time independent. What is the meaning of time independent here? Time independent basically means that even at some time t1, t2, t3, t4, this value of constant will always be same. Okay. So, it does not depend. Let us say for example, if I would have come as equal to some constant multiplied by t, then we would have said that it is a function of time, or let us say constant divided by t and so on, depending upon the integration being occurred. But because this integration was sure short, it was straightforward, we got a value of constant which is in the dimension of current, and it is time independent. Now, let us try to understand this more. So, now since this source has a EMF which oscillates symmetrically about 0. So, basically let me explain it. So, as you can see in the previous lecture, in the starting of the discussion regarding AC voltage with resistor, we understood that what are the typical movements of a AC current or AC source. AC voltage, basically these are sinusoidal waveforms. Okay. So, through which this is the voltage 0, correct, and this will be at some voltage V, and it is sinusoidally oscillating across 0 voltage, correct. So, it is positive for some sequence, and it is negative for some sequence. Okay. So, since this source has an EMF which oscillates symmetrically about 0, this current also oscillates symmetrically about 0, right. Very quite evident. This was also been explained in the first concept, in which we understood about the AC voltage supplied to a resistor, as in the value of current was coming out to be Vm by R into sin omega t only. It is also sinusoidally varying, but it is varying across 0 only, fine. So, this was the first concept I need to explain to you. Now, because this thing is occurring, what we can say, that there is no constant or time independent component of the current which is existing. What does it mean? It basically means that this constant, so basically to calculate further, this constant has to be 0 only. This is the only concept which I was trying to explain to you. So, let me just write everything which I just said. So, basically So, because the voltage being supplied oscillates symmetrically about 0, the current produced will also oscillate symmetrically about 0. That is, the current it sustains is sometimes 0, sometimes is oscillate. So, oscillate as in it goes in the positive cycle and it then retains in a negative cycle, and this thing keeps on moving, fine. So, because this thing is happening, so we can say that there is no constant or time independent component of the current which is existing. Hence, the constant in the above equation should be equal to 0 only. Why? First reason is that it is time independent, and second reason is that because it is oscillating symmetrically about 0, and hence the value which is only and only in the all the cases only and only value of constant which should exist should be equal to 0. So, these were the two reasons why. So, moving forward, so basically we got that what is I is nothing but equal to minus Vm by omega L cos omega t. Okay. So, now in the place of minus cos omega t, so using trigonometry we can write. So, we know, let me write it at like this. So, we know that what is minus cos omega t, that is equal to nothing but sine of omega t minus pi by 2. So, it is, so why we are doing this? We are just doing this so that everything should be in the form of sine only. Why we write, we need some sort of like this, because the initial assumption of voltage was in the form of sine omega t. So, as to get the relation, or so as to get a comparison between the voltage produced and the current produced, we are trying to change or convert this cos omega t into sine omega t. There may not be a reason to convert it, but just for a comparison sake purpose we are trying to change it into sine omega t. So, if minus cos, so this is normal trigonometric equation, and therefore, what we can write? We can write the equation of I as equal to nothing but I m sine of omega t minus pi by 2. So, this is the final relation which we require for the current purpose, that is nothing but I is equal to I m sine omega t minus pi by 2, where what is I m? I m is basically equal to V m by omega L, fine. So, this is the first derivation which we need for inductor purpose. Now, let us try to define some new wordings or new definitions regarding all these concepts which we just derived. Okay. So, now just let me write this equation again. So, what was the equation we derived? We derived basically the current produced is nothing but equal to I m sine of omega t minus pi by 2. Okay. First thing, where what is I m here? I m is basically the amplitude of current. Similar definitions as in which we did for AC current applied to a resistor. So, it is amplitude of the current, right. Now, a new concept came here, which is omega t minus pi by 2, and what was the amplitude of current? So, wait. So, it is let me first explain you that concept and then we can move forward. So, it is Vm upon omega L. If you remember correctly, what was in the resistor? It was simply Vm by R. That means this value of omega L which is obtained is sort of contributing or sort of in the similar sense as in a resistor type of concept which is being evolved in the inductor, correct. And that is why this quantity omega L is analogous to resistance, and it is also called as, please remember, very important, it is called as inductive reactance, okay, and it is denoted by, please remember this also, because when we try to understand the concept of series LCR circuit, these denotions are very important. So, it is denoted by capital X L. So, subscript is L, L stands for inductance or basically inductor, and capital X L. Okay. So, this is a new concept or new definition which we derived, that is omega L is basically called as inductive reactance. Why it is called as reactance? Because in the previous concept when we started to understand AC voltage applied to a resistor, we got the value of amplitude of the current as equal to Vm by capital R. If that was equal to Vm by capital R, that means this capital R is nothing but analogous to this omega L, or omega L is analogous to this reactor or reactance, and that is why we are trying to say, or we are trying to define a new concept or new definition for this omega L. This new definition of omega L is basically called as inductive reactance, and it is denoted by capital X L, fine. So, that was the definition required for this purpose. Now, let us move forward. So, let me just write again. So, basically what is XL? XL is basically omega into L, and therefore, what we can say? We can basically say what is amplitude of current again. So, amplitude of current is basically equal to Vm by XL, right. So, in the previous case scenario it was capital R, in this case scenario it is capital X L, fine. Okay, yes. So, that was the final thing. Now, let us understand more about this inductive reactance. So, the dimension of the inductive reactance is the same as that of resistance, and its SI unit is ohms, quite evident. So, basically omega L has a unit of ohms. Okay. The inductive reactance limits the current in a purely inductive circuit in the same way as the resistance limits the circuit current in a purely resistive circuit, quite evident, and that is the reason we are saying it to be analogous to reactance, correct. So, very easy terms, if a resistor is there we can directly put capital R, but if a inductor is there we will directly use omega into L. So, basically this concept of inductive reactance, what it is trying to do, it is trying to limit the amount of current passing through the circuit or passing in the circuit. Okay. So, the inductive reactance limits the current in a purely inductive circuit in the same way as the resistance limits the current in a purely resistive circuit. Okay. Please remember, when we are trying to understand this concept, we are trying to assume that only and only inductor is being installed apart from the EMF being produced. There are no internal resistances. Okay. We are trying to put everything into ideal case scenario. Okay. So, the inductive reactance is directly proportional to the inductance and to the frequency of the current, quite evident as you can see. So, what we can say, as we know that XL is nothing but equal to omega L, correct. XL is basically inductive reactance. This XL is directly proportional to omega and this XL is also directly proportional to L. So, it is only written here, what is written? The inductive reactance is directly proportional to inductance, as you can see it is directly proportional to reactance and it is also directly proportional to frequency of the current. Okay. So, that thing is also explained. Next thing is, a comparison of the equations for the source voltage and the current in an inductor shows that the current lags the voltage by pi by 2 or 1/4 cycle. Let us try to understand this line now. Okay. So, what happened in the case of resistor? Let us do a quick revision. So, in the case of resistor, in the case of a pure resistor being installed in a circuit, the value of voltage being passed through the source or EMF was basically equal to Vm sin omega t. Vm sin omega t, correct, and the current which was being produced was nothing but equal to I, which is equal to Im sin omega t. So, if you see clearly, the trigonometric equation or trigonometric form or the basically wavy part or variation part or oscillation part was same. It is sin omega t in voltage also, it is sin omega t in current also. This Im is nothing but equal to Vm by capital R. Okay. But in the case of inductor scenario, what is happening? If the value of V is equal to Vm sin omega t, if the value of V is Vm sin omega t, what was the value of current we are getting? We are getting the value of current as nothing but Im sin of omega t minus pi by 2. Okay. So, that is the reason you can see, due to this minus pi by 2 being occurring here, it is saying that what current lags the voltage. It is just saying that current is lagging the voltage. Okay. So, that is the reason being explained here. So, a comparison of equations for the source voltage and the current in an inductor shows that the current lags the voltage by pi by 2 or 1/4 cycle. So, 1/4 cycle, as in because the cycle is of 2 pi. So, therefore, 1/4 of the quarter is pi by 2 and then it is saying that it is lagging by 1/4 of a cycle. Okay. So, let me stop it here. In the next class, I will try to understand now what is the basic reasoning of understanding the phasor diagrams. We will try to understand what is being happening here, what are these diagrams basically being implemented. We will try to understand the basic crux of your phasor diagrams and then we can move on to the understanding of same concept for capacitor. Fine. So, that thing being said, let me stop the discussion here only. Thank you so much.